programming and security at the same sentence. Wow.
Okay. Hopefully that bit of power made my clicker work. So the first section of today, I have normal slides. The second section is about Spectre, and I'm still trying to figure out how to explain Spectre well, and it lasted forever to create these slides. So until I have a very clear explanation pattern, it's better to do it on the whiteboard. Also because there's a lot of motion involved. Everything we're going to talk about today is incomplete mediation. I know it says secure programming on the slide, but bluntly speaking, we have just rolled back to access control. Most of what we're talking about today is about failure of access control, or more specifically, how to get around access control. When I taught you access control, I was mostly teaching you to just think about what the different actions are. We talked a little bit about maybe how to structure access control statements within the computer, but we talked very little about enforcement. Now, I'm still not really teaching you enforcement because I'd have to teach you all of operating systems to teach you enforcement, but I'm going to teach you a couple ways that enforcement is broken. This is one of the side effects of having a breadth course. It's just, man, it's almost easier for the operating system professor to teach you access control than it is for me. These are all cases of what we call incomplete mediation. That means that the system is not fully checking. So when we talked about access control, I said there's this theoretical concept of a reference monitor, and no access should happen without going through the reference monitor. The attacker's goal is to gain access without going through the reference monitor, and that's what we're going to be talking about, how they can do that today. One example of that is what we talked about on Monday, stack smashing. Right? This whole idea of a buffer overflow or a buffer overread. This is mostly me reminding you. I'm going to start out with the common CVEs and CWE. I don't have a grease reason for putting this here, but if you're trying to, if you are attempting to understand different, security as a group, we want to understand the range of different bad stuff that can go wrong. And we want to communicate to someone else clearly what has gone wrong. It is sometimes taking me half a lecture period to explain to you a simple concept. And when you're trying to have an argument with a company about whether or not they do or do not have a problem, trying to give them a half-hour lecture is just not going to fly. So what we do is we organize known problems into specific statements that are linked to pages. And there's two groups that are commonly used. This is the CVE, Common Vulnerabilities and Exposures. This was launched in 1999 and maintained by MITRE. Fun fact, this was nearly killed by Dodge last year. It was saved at literally the last second when everyone claimed that they were just going to take it over into another country and the U.S. felt sovereignty loss. It's still controlled by MITRE and funded by the U.S. government. What this does is when a vulnerability in publicly visible software, this is the software most people are using or can use theoretically, when it's identified, it is given a CVE number. This means that when you launch, say, a patch or an error correction thing, even if you're not that software. So maybe the software is actually a library. And there's a lot of different groups that maybe all use that library. When they release a patch, they'll often say, this patch addresses CVE and lists the number. Nice, succinct way to very clearly explain what security issue this patch is handling. This is a global database. You can pull it up right now and take a look at a whole bunch of common vulnerabilities we know about. There's also the Common Weakness Enumeration database. Vulnerabilities are talking about a specific piece of software, so a specific case in which we have found a way to break into something, to a specific piece of software. Common weaknesses are common patterns, and in HSI we call them design patterns. They're just common patterns we see in code that muck things up. Buffer overflow is most definitely on this list. Buffer overread is on this list. I will talk in a minute about something called use after free, which is on this list. These are all just common mistake patterns that we see. I could probably do an entire course on secure programming doing nothing but going through the common weaknesses. The difference between common weaknesses and common vulnerabilities is common vulnerabilities are a specific tech and a specific piece of software. Common weaknesses are general problems that we see in many pieces of software. It is very common for a common vulnerability to cite a common weakness, and the other way around. So in this case, I grabbed this last year. This is a common weakness called use after free. My mouse is just not happy today. So in the common, this is CVE. You can tell it says CVE at the front. There's one down here that says timers are not disabled when related object is deleted. And this is CVE 2010-17 or 1772. And there's a whole write-up explaining how this particular piece of software is having this problem. What they're actually talking about, if you scroll down, is a common weakness called use after free. I'm going to very briefly explain use after free. Okay, reorienting. So we talked previously about a buffer overread and a buffer write, but an overread and overwrite, you're kind of looking at contiguous memory, and you're looking at maybe trying to read someone else's stuff. This is a case in which maybe an attacker can use it, but actually the more dangerous case is that you're harming your own program. The idea is you have two processes, process one, process two. Process one creates a pointer to a memory address, A, and allocates memory there. You can kind of see that near the top, this char statement. Again, I do not know why my mouse is upset today. And then you free the memory, but keep the pointer. So you see here this statement, if error, put in an abort equals 1, and free the pointer, right? Pointer is free now. I know not everyone here does C, but this means that we've basically told the operating system, I don't need this memory anymore. Go use it however you feel like it. Process 2 allocates that memory. So process 2 creates we're looking at kind of a race condition here. So process 2 goes, there's some free memory. I think I will grab that and associate it with a pointer. And then what happens down here in this last line? If abort, which is now 1, log error, operation aborted before commit pointer. What are we pointing at now? Are we pointing at process 1's stuff or process 2's stuff? 2. So if process 2 has gone and written some data in there, we're now reading it out. This is a simple example of something other than a buffer overflow where you can end up in a situation where you're reading another process's memory. Now, the operating system will try to get involved here, depending, again, there's so many operating systems. But imagine doing this within your own program. So what I'm putting out here is to get you to start thinking about where the edge of the access control enforcement is. When you think about read, write, execute, you're thinking a lot about files. What about memory? Where's the read, write, execute on memory? We do have it. It does exist, especially if you're reading that memory out of a file, then we have to transfer those access control permissions with that into chunks of memory to tell us whether or not you have access. But if both of these processes are your program running under you, the user, are they locked out?
Well, with most modern desktop processors, we're not talking about the vendor world where things are more simple. You have virtual addressing.
So virtual addressing will not save you here.
Not within your own program, but it wouldn't be more likely to save you from another program accessing that.
Yeah, so when you start getting between two completely different programs, this gets tricky. But imagine this is one program or even two threads within a program that are all encompassing. But this thread is user 1 and this thread is user 2. Because often programs do access control within the program, not just within the operating system. So this becomes possible now for this thread to potentially read data out of that thread if there are two users within the program. This is a wide classification of issues. It's a common weakness. I'm going to spend almost all of today on side channels. So we're going to start out by explaining what on earth a side channel is, and then we're going to talk in depth about two of them. One of them is called rowhammer, which is a bit easier to explain, and the other one is called spectre, which is going to take a lot of whiteboard work. A side channel is a way to learn a fact indirectly. The most classic example of this is the Pentagon likely to launch an attack tomorrow? Well, how much pizza has been ordered to the Pentagon tonight? This is a side channel attack. There are a lot of other examples. Maybe I want to know your password. You've walked off and you've locked your computer. By the way, I wander around here sometimes during Think, Pair, Shares, and a lot of you surprisingly do not lock your computers. Anyway, I notice I could use thermal imaging because your fingers have heat. So you can see someone log in and go, oh no, I need to go somewhere else. Control lock, walk away. You can use a thermal imaging camera, just see what the different characters were. This is a small space to break, even if your computer is doing lockout. You can use things like temperature. So that computer across the way is running OBS, and oh my goodness, that is damaging its processor. If you point thermal camera images at it, you can tell that it's doing a lot of work. Now, if you're trying to figure out a fact, like which of these computers here is doing a lot of work, and maybe this computer is running line 1 of a transit network, and this one is running different things, you can tell just which of the computers are currently active, again, with a thermal cam. Radio waves. More power being transmitted over a wire will emit more RF. I have seen amazing attacks. These aren't side channels, actually, now I think about it, but in which they basically just send messages to cars. So if you have an EV and you've plugged your EV into a charger, what happens when I run a whole lot of power across a wire? What do we call that?
Charger?
An antenna. A whole lot of power run across a wire is how we do radio broadcasting. So what do you think is happening with all the signals that car is sending back and forth to the charger? They're being broadcast because they are being run over a wire that is highly charged, which means that you can also inject messages. I have this, anyway, some other researcher has this video of just driving his car along and just shutting down all the charging on every single thing as they're driving because he's just sending termination requests that are being picked up by this enormous wire. So radio waves, power. I've seen amazing attacks where they take, the power meters today do very fine-grained sampling for your house. So how much money do you have to pay for electricity? So they'll do fine-grained sampling. You can actually use an advanced meter of this nature to figure out what TV program someone's watching based on the sheer amount of the light that's emitted by the TV. Takes more power. Dark doesn't take as much power. So within a small number of possible shows, you can differentiate which one the person's doing, and you can figure out what odds are which different appliances on within the home, just using power. It's a scary world out there, I'm sorry. You want to know the Swedish Prime Minister's home address? Pull his bodyguard's running data. Smartwatches like this, particularly ones marketed at people who are into health and exercise, by default usually share the data on Strava. And if they have not turned it off, you can get beautiful maps. Maybe you notice that Google Maps won't show you military bases. It looks like a big fuzzing thing. Maybe you don't notice these things. I notice these things because I'm in security. You pull up this thing and it looks like a big fuzzball. Put it up in Strava, it looks like that. Because if you're in a military base, where are you going to work out? And if you have it default on to share data, it's public. These are all side channel attacks. These are all cases in which the system itself has never been hit. And instead what's happening is we're finding data that's sitting just to the side of the system. Often it's a side effect of the way the system was functioning. Yeah.
So the base thing, that's a one-off, that's a
No.
Well, no, I mean, but like...
Pick your favorite base.
I understand that, but like, it's going to happen once the data's out there. Damn, like, that's unfortunate. The Pentagon pizza thing is just now a joke.
It is a joke.
So but it's still happening. So why aren't they running their own catering? Like, you know what I mean?
They do run their own catering.
Right?
I don't know if you know the shape of the Pentagon.
Yeah.
So obviously it's famously a pentagon, but what's the middle?
The hot dog stand or whatever.
All the food courts are in the center of the Pentagon. So again, if you have a thermal camera or a satellite, these convenient things, you can really easily tell whether the food court's on. This is admittedly a joke, and if they're really determined about it, they don't. Honestly, I think Trump is doing work from home because they don't care about security.
But the pizza thing was based on a pizza place. Like somewhere else in DC.
Well, so the pizza thing was based on this concept that there are famous pizza places in DC, and you can call one up and figure out whether or not you can get a pizza.
Alright.
And if you can't get a pizza, a lot of pizzas have been ordered. This is also, there's several attacks done against Bromley Park, I'm mispronouncing that, in the United Kingdom, which is where a lot of the cryptography stuff was done. Looking at things like, because the programmers at that point in time were all female. And so and they were usually living together in groups, and so you could see when they all went in just by sitting there. I mean, there's a lot of things you can do where you have to be very creative and kind of think about the process. But what I'm basically talking about today is how to do this remotely at scale. But the main point is you have to think about is that we're not attacking the thing. We're attacking the side effect, its shadow almost, that it leaves on the world. Also, just as a security professional, if you're actually trying to secure a system, you have to think about stuff like this. I remember they had the chief security officer for the CERT in Denmark come in when I was studying in Denmark. And he described the situation where somebody had built this beautiful server room, like highly enforced door. What do you think the walls were made of? Drywall. What'd someone do? They took a motorcycle, ran it in through the side of the building, smashed straight through the drywall, took the server, put it on the back of the motorcycle, drove off. You think this is the end of the story. They got the wrong server. So they came back the next day and did the same thing again because they hadn't fixed the problem. Keep in mind, at that point in time, encryption was rare. You really do, when I talk about attack surfaces, this is included in an attack surface. But this is also a threat model. How many of your friends are actually walking around with thermal cameras? In this department, maybe you actually know a couple, but in the general world, it's not a common thing. All right, so we're going to talk about row hammer. So if I take two wires, wire 1, wire 2, and I run them next to each other, particularly for a long distance, you start getting what's called resonance. Now, if you're an EE, you're thinking to yourself, oh, that horrible thing called resonance. We try to stop that because it mucks up all our signals. If you're in security, you're thinking, that awesome thing called resonance. That's how we steal data off the neighboring wire. So what happens in resonance, and apologies, I let ChatGPT make this diagram. I think it is actually accurate. But the main concept is that if you have two wires running next to each other, what is wrong with my mouse? Okay, if you have two wires running next to each other, they create basically they have a signal, right? And then that signal, if it's not well shielded, hence why we shield wires, it can transfer over into the neighboring one. Again, what do we call this? A radio and a receiver. Because what's a radio? It's a high-powered wire that has a bunch of stuff on it that's not shielded, so that it does send out radio waves. All right, basic concept. Now we're going to dive into a processor. This is the main concept behind row hammer. So you probably haven't thought about it, but your computer runs on electricity for a reason. And so if you look within your memory, like things like RAM is tightly packed. What does that mean? That means there's a little electric thing here and a little electric thing right next to it. And how much shielding is sitting in the middle? Not much, because we're jamming that in as tight as we can get it because we want speed. Now, it won't naturally resonate. It's not a really long cable like I was describing a moment ago. But you can make it resonate if you're persistent. So the idea behind row hammer, sorry my mouse is not working. See these two yellow rows? Imagine that you can get access to those two yellow rows. You basically put access, these are, no, this is RAM. So these are two rows in RAM. So you have access to two rows in RAM. And you just repeatedly write the same thing to them. Just over and over and over and over and over and over again. In fact, if you look at this, it basically says write to X, top yellow, write to Y, lower yellow, clear them both out, do it again. And just keep doing this really, really hard. You will change the content of the purple row. This is the main concept behind row hammer. It's not very complicated, but it is very problematic. Because now, what happened to our access control? You had access to yellow. You don't have access to purple. We didn't give you access to purple. Now you are able to write into memory of another process. And that is a problem. But you may be sitting there thinking to yourself, I'm just going to try to preempt a question, how on earth do you create this memory organization? Because this is tricky, right? You have to have this exactly aligned in order for this to work. And your victim has to be sitting in the middle of your memory rows. And so this was originally proposed as a research paper, just going, look, you can totally do this, but we have no idea how anyone could actually pull this off in real life. We're researchers. It's fun to do weird stuff. There was a question in the front.
I was going to ask you if ECC RAM less vulnerable to this.
I would not know. I am not deep enough in the difference. This is done with DRAM. I do not know if ECC RAM is more or less.
It's just DRAM with ECC, like your repression codes built in.
No, it would not, because you'll see in a moment. Because you can control all of those bits, not just a random bit, you're writing a full statement in.
Oh, so you're able to actually...
You can change the full row.
But you can control what you're changing it to, or is it...
Yes.
Oh, okay.
Yes, you are controlling it. So that what you're writing to the two yellow lines is the same thing.
Yeah.
And that's what you're trying to put in the purple.
Okay.
So you can write exactly what you want to into the purple. It's not a random thing. You're not dumping random stuff. It's an exact thing.
Now if the purple, if the right times are not consistent, then ECC would work.
No, the write times are consistent because odds are high that these two move instructions will appear next to each other. And you're running this 10,000, 3,000 times. I don't know how many thousands of times, but you're running this a lot. It's called row hammer because you are hammering. You're hitting it not once, many, many times. So if you got unlucky for half a second and you didn't hammer on both sides, that's fine. You'll hit them again in another 1/4 of a second. And this will change that purple row. So how on earth do I actually do anything useful with this? Because it's not useful, is it? Okay, there it is. All right. For those of you who have actually taken operating systems, you're probably more up on what I'm going for, and I'm sorry. The same apology I gave to you when you were doing networking to the other half of the class. I am oversimplifying things in order to go deep dive on one topic. Pages. So we talked about in networking how we put everything in packets because they're convenient. You can every computer can handle the packet. We don't worry too much about what's in it. In memory, we put things into pages and into what we call cache lines. So the idea is we organize all memory into blocks of the same size. Now, if whatever it is doesn't fill up the page, well, you just got some empty memory at the end. It's the case that everything is organized into same size chunks. And when I move things in and out of RAM, and when I move things in and out of cache, I move them in and out in consistently sized chunks. As software engineers, you're probably very familiar with bits, bytes, words, pages. A page is, I think, about 4 kilobytes, but this depends on, again, operating system, etc. In this example and in the next one, we're assuming it's 4 kilobytes. So one of the things that was mentioned earlier is this random address randomization. So you can see this picture here of the stack and the heap, and you notice these are all contiguously listed as 10, 11, 12. But if you go onto the physical memory, they're all over the place. That's because you can kind of load them in one piece at a time and create something in RAM that may seem contiguous when it's not the same on disk. And you're just handling memory in these chunks. This is very important for making row hammer function. We've started doing a lot of processing in the cloud. When I was young, we did a lot of processing on clients. When I was really young, they did a lot of processing on servers, and then they moved it to clients. Now we're moving back to servers again. That means it is quite possible that two companies that are not friends are on the same CPU. It's quite possible they're both running on AWS. It is quite possible they may think they're in their own VM, when in fact they are in their own VM on the same system. The processor could not care less about access control. The processor cares about speed, 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 speed. Other things care about access control, and they communicate with the processor about it, but the processor itself could not care less. It takes data in, it processes it, that's it. So one of the things we do in order to do speed is we do memory deduplication. The C library is the C library is the C library. Why would I have 12 versions of it on my processor when I could have one version of it on my processor for 12 VMs? Because I want to put 12 VMs on one computer so that I don't have to spend as much money as a big system. So things like libraries, for example, I really want to collapse them down into one page of memory that a whole bunch of things point to. All right, is this sort of making sense? There's no attack in what I'm describing right now. It's a normal process because they are only doing this for identical pages. What? Huh?
Even across users?
Even across users.
Across virtual machines. That's horrifying.
Yeah, but it's safe because you're doing it with only identical pages. That's a sneaky trick up here. So the idea of this is memory deduplication allows an attacker to reverse map any physical page to a virtual page she owns. What if I forced my victim to have an identical page to me? This is meant to happen for things like libc, where it's identical naturally. But you don't want to go around chasing every weird library the programmers have found this week. So instead, what the system is doing is just looking for identical pages. And the statistical odds of two pages being identical for two different programs is quite low. So it's just looking for identical ones so that it can collapse them. So imagine, okay, there's a whole diagram up here. We have the host's virtual memory, the victim's virtual memory, the host's virtual memory, and then the attacker has some virtual memory. And so what we can do now is we can use rowhammer to force the victim's page to look like ours. So now what I do is I get the victim's page into memory. I put the rowhammer elements in. I change the victim's page to look like my page. I don't care what their page originally looked like. I just want to change it to look like my page. Because if I can change it to look like my page, C happens. C happens. It becomes the case that in the actual physical memory, both of these are now pointers to the same spot. Now, if I can edit my memory, I can edit the victim's memory. What I'm describing right now is academic research and less in the wild attack. Actually, I don't know if this was or was not found in an attack. There's a third paper I'm not talking about here, which is how do I actually get that lining up to occur in memory where I can sandwich the victim. And the short answer is that with some work, I can actually encourage a victim's cache line or RAM row to go into that one slot. It is possible to do statistically often enough in order to pull this off, at least in lab environments. All right. I think that's... Okay. Any questions on rowhammer before I dive into the deeper issue of Spectre?
If the memory changes, but the cache doesn't change, would it be treated as a cache corruption or a memory corruption?
Does it matter? It's not corrupted. From the operating system's perspective, it's not corrupted at all.
Ah.
It's normal. It's exactly what, no access control is broken according to the operating system.
So for these physical vulnerabilities in hardware, is this more of something that falls more towards the people designing the architecture in terms of from the logical level, or would it be more of something that the electricals, like on the transistor level and on the place around?
Neither of these are... Okay, so if you treat speed as the pinnacle of the goal, and security is this thing below speed, this is unfixable. You can do it not necessarily at the straight up hardware level, but people who work at a very low level can target that paper I didn't cover, the one where it becomes possible to kind of encourage that positioning. If you can discourage that positioning or make it much harder for someone to do that, then the whole rest of this falls to pieces. But I really like Rowhammer because it's much easier to understand than Spectre. And it has a very clear link between both hardware and how software works. And it's one of these things where this isn't so much a side channel as its ability to write. But again, it's coming in kind of from the side position you're not thinking about. All right, Spectre. There are actually two vulnerabilities that are almost always described together. One of them is Spectre and one of them is Meltdown. When I try to describe them together, I confuse everyone here. So we are going to only talk about Spectre. We're going to talk about Spectre because, honestly, I understand it a bit easier, and I think it's a bit easier to explain. And also because Meltdown is fixable to some degree, and Spectre is not fixable.
Hold on. Could you go back to the pages diagram? So the idea is that we're going to make our memory look the same as the victim memory. We're going to make our memory look the same as the victim memory.
Yeah.
And then we're going to write to our memory.
Yep.
Which at the same time writes to the victim memory.
Yeah.
This is horrifying.
Or I wait for the victim to write to the memory and just read it.
And well, we can't. We don't
This
do
is
that.
more fixable, potentially. I haven't looked actually into how they're fixing this, but this is an efficiency move done by hypervisors.
Yes.
But it's a decision they are making. Now, it is possible that, again, I have not looked into the fix. This is from 2016. My guess is that they have made some adjustments. A basic one would be to start having more persistent understanding of what can and cannot be collapsed. But it's more work to do. All of Spectre, okay, so Spectre has two variants. We're focused on variant 1 because variant 2 is harder to explain. Variant 1 is explained entirely with those two lines. We're going to be spending quite a lot of time on those two lines. The idea of this is called a timing attack. A timing attack is a situation where I'm almost exploiting a race condition. I'm trying to understand how fast something happens. So not Spectre, David Brumley at Carnegie Mellon famously broke RSA crypto. How did he do it? He realized that if you send a message to a server that is using their private key to encrypt or decrypt something, and you send the message in a certain shape, you can turn it into a binary search. So the server will respond at a different speed if you send, I'm making this up to make it simpler. If you send all A's to it, it will respond, how do I explain this? Basically, the value of the private key, if you are sending a message that targets above it, it'll go slower. If you target below it, it'll go faster. And he was able to turn finding a private key value into a binary search. Because at any given time, he could send the server 2 packets to encrypt, and based on that content, he could tell whether the key was above or below a certain value. And then you just keep doing this, and now key finding is a binary search activity. And this broke RSA. This is a beautiful example of a timing vulnerability, where what your focus is on is not the content, it's the speed. How fast can I access something? And does the speed of being able to access it tell me anything? I'll give you another example off of, say, passwords. Imagine I tried to guess a password. And if the person's password is only 1 character, it comes back really fast, yes or no. Even with no's, it comes back fast. And if it's 27 characters, it comes back really, really slow. Again, yes and no come back slow. Now I can go and run a quick password attempt against every single user on the system. I can isolate it to the users that have character passwords of below, say, 4, and spend all my time there. There's a lot of things you can do with timing attacks. This is a timing attack. The idea here is you induce the victim to okay, I'm going to read this, and then we're going to spend a lot of time explaining what I'm talking about. You induce the victim to speculate and perform operations that would not occur during strictly serialized in-order processing of the program's instructions, which leaks victims' confidential information via a covert channel to the adversary. And just to get this point through, because it's going to confuse everyone, this is a slow attack. You can read all of memory, but not as one chunk. You get to read it 1 byte at a time. But you can still read all of it, which is terrifying. I threw this slide together 2 seconds before the lecture, and then we're going to move to the board. Hopefully everyone in here realizes that the code you write is not the code that executes on the processor. Even if you're writing in Python where there is no compiler, there is kind of a compiler. It still has to convert it into machine instructions. So I have only 2 lines there, but there's a lot more here. Hopefully you're also familiar with the concept that the order of instructions you put in your system is not necessarily the order that the processor does it in. The processor is fully welcome to reorder things, and the compiler is fully welcome to reorder things. Compilers regularly reorder things because the whole point of the compiler is to make stuff faster. If you were stupid enough to write, like if A equals B, set C to 10, and then you put that exact same code block down 4 lines below, but you don't touch any of the variables in the middle, it will just delete one of them for you. Your code gets mucked up, just like the compiler will readjust the heck out of your code. And once you hit the processor, its goal is speed. As a side effect, it will happily reorder your instructions. So what if you do a check, so something is trying to prevent you from accidentally causing a problem, like an array out of bounds check, like we just talked about with the buffer overreads, and then you access it. Is it guaranteed to appear in that order? No. It is entirely possible that the processor will read something before it does the check. And that is the cornerstone of this attack. So, by the way, I do not have think pair shares, but I may just come up with some as we progress to try to talk about it. To understand this, you need to understand memory, and this is where we kind of start spending a bit of time. In this story, we have 4 types of memory. We have disk, we have RAM, we have cache, and we have registers. And they are ordered in speed. Disk is really slow, like glacier speeds. RAM is also slow. It is not anywhere near as bad as disk, but it is slow. Cache is faster. We're starting to get a little bit more snappy, but by the time we can actually get a cache line loaded, we could have executed 20,000, a whole lot of instructions. And registers are fast, really fast. We can get these things like snap, snap, snap at the speed of the processor is going. Processors want to go fast. They want to process as much code as possible, but they're living in this annoying world. These things cost money and they run up against physical limitations. The amount of data you can fit in a register is teeny. The amount of data you can fit in a cache is bigger, but still pretty small. The amount of data you can fit in RAM, now we're actually hitting this point where we can start, like, when was the last time you could update the amount of cache you have on the computer? You really can't, because it's very physically limited. RAM you can update more a little bit, but it's still pretty limited. And then you go out to a hard drive and you can have as much as you want. So we're dealing with this balance of this problem between speed and size. Ideally, we'd have everything on the fast access, but we just can't fit it. So what happens is you have a processor, and it's executing instructions. And then you have registers. And these are, for the purpose of this conversation, on the same chip as the processor and are super, super fast. There's also not many of them. Then we have cache, RAM, and then disk. For those of you who've studied operating systems, you're probably aware that if we had to go out to disk, everything has gone wrong. But here's this problem. You're happily executing along as the processor, And how do you even know what you need next? Because, oh goodness, what if this over here on my instruction set, A equals B. So if A and B are both living in my register, this is so wonderful. I put A and B, I'm all happy. This was so fast. But what if B is sitting all the way over on disk? Glacial speeds. Now I must send a request to disk. Disk must send the data to RAM. RAM must send the data to cache. Cache must send the data to the register. And by then I could have gotten so much done. This means that in the operating system and in physical memory, we're continuously doing what's called prefetching. We're guessing. And there's a lot of hardware that kind of sits behind this, in which it's continuously trying to guess, what am I going to need next? One way it does this is it looks at historical patterns. So especially if you have a process that is run many, many times, it will start building an understanding of what that process access patterns look like. If it grabs page 1, it probably wants page 2. RAM has a lot more space than, say, registers. So what will happen is out in this zone, it will try to guess what pages it thinks you're going to need next. So if it sees A equals B over here, or if this command happens a lot, it will load B preemptively to try to speed things up. This means that things you never even wrote in your program are happening in the computer because it's guessing. It's saying, there's good odds that I will need B. Let's start doing that right now so that by the time the processor wants something, hopefully it's sitting here, maybe if it's sitting there. We don't tend to move things into registers unless we're really certain because there's just so little space. But we will start moving them into RAM and cache. And so this is, we still haven't hit speculative execution, but I'm trying to get you this concept that we're doing stuff out of order and we're doing it for speed. Now imagine I wrap this in an if statement. If A is greater than 4, what's the system going to do? It doesn't know if it needs B. Now maybe you could do a look ahead if it's just a straight set of instructions, but does it need B? Now maybe it needs potentially B enough to load things into RAM. We've got a lot of space there. Maybe we'll just load B. Maybe it's a good idea. But what about these later stages? Worse, maybe I knew I needed B, so I've put it in maybe cache. But B wants me to do some complicated computation. Maybe I want to take the log of B times 453 for who knows what reason. This is multiple lines of a machine instruction, isn't it? I have to load B in, I have to run a logarithmic computation on B, and then I have to do an addition. For those of you who are used to kind of machine instruction, you're thinking, that's like several lines of code that the processor now has to operate. This is slow and this was fast. I don't really want to switch out all of processor memory. So when processors hit an idle moment where they can't make progress, they have to switch out all of their memory to basically a little storage area and swap another process in. This is sort of expensive time-wise. I don't want to do that. So what we do is we do something called speculative execution. If the value of A is not known yet, if A is not sitting in this register and B is sitting in this register, and maybe A is sitting down here in RAM, what will happen is the system will guess. It will say, what are the odds that A is bigger than 4? And usually it will use past experience. So again, I'm skipping a lot of stuff on hardware and how this is done. But it will look at this branch and go, historically, the last time I went through this branch, the last 6 times I went through this branch, which way did it go? And if most of the time A is greater than 4, it will skip this and just run that. All right, we're still here. So what will end up happening is it will compute the output of this. Again, if you use machine code, it won't directly put it in A. It'll take the output of this and put it in a register. So now we have kind of A, but this is a dirty A. This is an A that we know is different than the A sitting in cache, or the A that's kind of heading in this direction. So we'll kind of have A prime just sitting here, waiting to be copied over into A. Then this comes in, and it turns out this A is actually 2. Well, drat. We just ran this whole computation. Turns out A is not 2. Worse, we've actually kind of muddled with our registers here and already done the computation. Now what? So then what it does is it does a rollback. Or if it turns out that A was 5, we would just move forward. Nice and easy. If it turns out if this branch is wrong, what happened is when it did the speculative execution, it did a little quick copy of all its registered values because it knows it's guessing. So the moment it does this, it goes, well, I actually don't know what A is, but this is B, and this is what the value here was, and we kind of copy it into a side thing. We run the speculative execution. If it turns out that this comes back as false, that we can't take this branch, then we copy these values back over. And then A becomes whatever it was here, 2. And we pretend like that never happened.
It did never happen.
All right. Let me think of a think pair chair around this really fast, because if I don't, we're all going to get lost. The whole point here is that when you have a branch, what happens on this side, what happens on that side. So let's say, I'm going to change some of these values. All right, so let's say B equals 5. Let's change this from a logarithm just to make everyone's lives a bit easier. So let's say B times 4 plus this value. We're actually going to set this into C. C is currently blank. We don't have a value. Actually, we'll just set C equal to 4. And A is unknown. A may even be living over here in RAM. C similarly would have been copied over this way. All right, so imagine that I speculatively execute this. I'm going to assume that A is greater than 4. We're guessing. It turns out A hiding over here is actually 2. What will the state be after I execute this branch before the rollback, and what will happen after the rollback? So 2 states. I want to know what happens if after I finish executing this line, and then the second state is what happens when A comes back. And we learn that the line is wrong. So try writing both of those down in terms of the register values.
So for this, are we assuming branch prediction but in order execution with?
Well, there's only 2 lines here, so you don't have to worry about in order execution.
Well, because of what would be around it, that's why.
What would be around it?
Like, what I'm saying is, we still have like the branch that's predicted, but there's other things, like, if we didn't have a completely clean bytecode, and there was other things, like other instructions in there, there'd still be other things going through.
Yeah, you're thinking about the fact that a processor is processing more than one at a time, and we don't need to worry about that statement for this. So we're going to just assume it's only processing one at a time. Whether it does that or not is irrelevant to this attack. If you don't understand what I just said, that's okay. What I mostly said is we're ignoring what it was said. So we're all fine. I want to know 2 things. I want to know these register values after line 2. I want to know after the alpha value is loaded into registers. So what are these registers after line 2 or after, and then again after we discovered that this is wrong? Go ahead and try to write it out, and I'm going to wander around. I'm trying to figure out how confused people are.
We're just naming the registers A, B, and C.
What's in the registers? we're just calling them A, B, and C, or the lines on the whiteboard.
Say how deep is the pipeline?
We do not allow the registers to write back to the cache before this comes back.
Yeah.
This makes some sense because if it's going to be that long, it'll just archive the entire thing the CPU is working on and work on another process.
Yeah, I was just curious as specifically you just squash whatever is in the pipeline through just a very simple like single instruction, no out of order execution. One single
Pipeline in instruction.
one instruction being issued per cycle. 5 the classical 5D pipeline, so the fetch decode execute memory there's 5, and basically it was kind of a race prediction. In the case where it misses, it would just be the idea of just squashing.
Yeah, you squash the later.
Yeah, but
Okay.
you make it such that you never actually get to the memory or the right stage before you know that you missed. It was simplified because we weren't interacting with this and stuff like that.
All right, I'm going to try to summarize. The first row is asking about. A lot of it involves the architecture class, so I'm going to skip that part. In this class, because we're just dealing with things simpler, we assume that it's never the case that the registers write to the cache. So what will normally happen is it would run all these computations, it would come up with a new value of C, and then as it's progressing, one of the things it might do is write back to the cache. This is how a normal operation works. For this attack, that is not necessary, and we're just going to assume it doesn't happen. That it's always the case that we don't write backwards until the speculative execution comes back.
I'm not even talking about, we're going to talk about like writing to the register file itself.
I mean, because it's got a shadow register file. Because it's got. I do not want to get that deep.
Okay.
That is the short abbreviated version. So the way processes work and architecture work is actually whole classes for a reason. I am making a lot of simplifications here, but I'm being very careful around certain lines. So a couple very careful things I am doing is one, is this progression that when you call something, it progresses through everything. That in speculative execution, we never hit the point where we write back to cache. The processor will not push things back to cache until it's certain about the outcome of these branches. And so we're always in a safe condition because it's always the case that, let's say, all right, this is not very attack-like. This is normal. What happens if I do something like A equals victim address? All right. So I've just written a line that just says, now take something at the victim that I do not have access to according to the access control lists inside the operating system. I want you to put them in A. Machine code looks a lot like what I showed you, right? There is no magic secondary check for things. So why is it the processor doesn't just do this? Well, the answer is that sometimes it does this, or it starts doing it. So it will go and do things like take that victim address and go, well, does it happen to be sitting over here? And so I may speculatively load it while I wait. And then I might even do the computation you asked about, maybe put that over here. But it never gets written back this way, and I never allow access. Okay, I think I've gone too far off of the stuff I'm not actually needing to explain. The cache and the RAM have another process that makes certain that only things you're allowed to have access to are accessed. But that process, when you send the read request to it, might come back with that yes or no slower than the data came. Okay, sorry. I'm explaining this different than last year, so I have to catch up with myself. cache is contiguous memory. It's a chip, right? There's a contiguous physical memory. This whole virtual memory thing, that was living over here. Over here, we're dealing with the actual memory addresses because we want to go fast. We don't want to be looking magic, stupid address looking up at the time. And there's some remapping going on I don't want to talk about. So it is entirely possible that you make a request. You say, Alpha, I want to go and take this thing that's in the cache, and I want to go and put it into the register. And this is what I was trying to understand just before this class, what actually stops that. And there's a processing unit that goes and double checks these things, but it's in race condition. It's very similar to the speculative execution I just talked about. It might happily load it, and then a check comes back and it goes, oh, actually, no, you're not allowed to have that thing. Let me just take that back out again. And redo these registers again. So the processor is frequently kind of running ahead of itself. It's maybe guessing on this if statement and then doing it. Maybe it's accessing a bit of memory and then deciding, no, later I'm not actually allowed to do that. I think I'll roll that back. Because these checks take time. And sometimes that's happening. I think a lot of that is actually happening at the later stages, where maybe I compute something and then I can't persist it. All right. Now we actually hit these two crazy lines. This is a timing attack. So there's a reason I've drawn all of these on the board, and I keep drawing arrows everywhere, even though you're going, Cami, it does not matter. I had to copy this from disk. Why are we doing speculative execution to start with? We're doing it because of speed. If we had access to A, we would have done this faster. And so the problem is that we don't actually have access to it for some reason. This works because this causes speculative execution because it's not in the cache. This is a timing attack, what we're about to talk about in Spectre. So this works because it's slow. If it was fast, we wouldn't need speculative execution. So if A was already loaded in the register, there would be no speculative execution. We just go. This only works because it is slow. Speed is something I can measure. So I can actually measure how slow something was as a programmer. So I don't, again, want to get too depth of that. But you can measure whether or not something is what we call a cache miss. So let's say your code is happily executing along, and then it experiences what we call a cache miss. A cache miss means that I want to access A, but oh goodness, A is not here, so it has to be loaded from RAM. Loading from RAM is slow. I can measure this. So the point of this attack is that if I execute the attack, it causes a change in the drawing up here. So if a... Yeah. All right, I'm just resetting things so that we can go through this tiny code example. All right. If I'm executing this, and this is what my registers look like, at least in regard to this, what's going to happen? Well, I try to execute A, but I don't have A. So I'm going to put out a request, and A is going to start slowly progressing over here. I don't have C or B either. That's annoying. So I'm going to put in a request for C and B. Eventually A comes back, eventually B comes back, and eventually C comes back. And they'll be then, and by this time, A maybe comes back, and I go, drat, A is out of bounds. I shouldn't have taken this branch. I will stop worrying about this. I'm not going to execute C and B. But these processes have already been initiated. And so we go and we go ahead and we copy from RAM, which is very slow, has already sent B to cache. RAM has already sent C to cache. The CPU doesn't want these values anymore, so it doesn't try to load them. but they're now sitting in cache. So this is what it looks like if speculative execution was done. And this is what it looks like if speculative execution was not done. These are different. So what happens, these are fine. This is the part that was changed. So what happens now if it looks like this? Well, what I could do is down here, I could run a test to see whether or not I'm going to have cache miss. So I can actually test, okay, try to fetch B and just see how long it takes. If I can fetch B fast, then I know the speculative execution happened, don't I? If I have to spend a long time to fetch B, then I don't know if speculative execution, or if it takes a long time to fetch B, then I know that speculative execution did not happen. All right, what I'm just about to describe is not Spectre. It's actually closer to Meltdown, but it kind of helps you along the understanding of that, which is far more complicated. Now imagine I did this with two if statements. And let's say the code up above made absolutely certain that A is not loaded. You can call things, for example, that will clear A out of cache. So I purposely made certain A is not loaded. Therefore, I know that there's going to be a speculative execution here. I can also train the processor. So I said that it's doing this statistically. So if I can go and convince the processor that the A is less than 4 most of the time, it will speculatively execute. And I'll come back to that in a moment. But let's say that we know it's going to speculatively execute. And let's say that, again, we have made certain that B is in cache. Okay, this is a bit complicated with B, but let's just, I'll come back to how we did that. But we know that B is in cache, and maybe C is under our control. So we've set it up like this. B, however, is the victim's variable. We do not own it. C is ours. We have no business accessing this. So now what's going to happen, sorry, C is ours, but it's not in cache. So when we start executing this, we're going to have to do branch protection because A is not in cache. We're going to be able to do this if statement fast because B is in cache. And C is not in cache right now. But in order to do this, we need it to be in cache because otherwise we can't make sure we're not going to cause a problem. Or maybe a C times C, for example, just to make sure we need C. It's very important that C is not in cache here, but that we need C in order to do this computation. So now let's say we speculatively execute. We guess that A is less than 4. We then look at this. We know what B is because B is already in cache. We can go faster on B. So we can figure out if B is greater than 3. If B, well, you can add an else here. This is clear with an else. If B is greater than 3, we're going to write to C. So we're going to initiate this conversion with C. If B is not greater than C, then we're going to do the same thing with D. In this case, let's assume that B is 5. Since B is 5, we're going to initiate this. Then we kind of create C prime. Maybe we write to C or some in the registers because it's coming across to the registers. We create a temporary C where we've marked this as needing to be 7 times itself. And then we kind of get down here, we realize, oh, drat, A is actually greater than 4. So now we roll back. We reset all the registers back to their original value. No harm, no foul. All the data's been erased. We don't actually know now it's E. But what's happened?
Slow down.
We don't erase this. We don't clear the cache. Now what do I do if I'm an attacker? I check both C and D. I send a request now, just load C, load D, see which of them comes back faster. Which one's going to come back faster? C. If C comes back faster, what do I now know about B? B is greater than 3. If D came back faster, what do I now know about B? B is less than or equal to 3. What have I just defined? A binary search. All right. I'm going to pause here and let people think about this because this is necessary to understand the next step. This is a timing attack. The attack is your ability to determine whether or not something has been loaded in cache. And it's based on this speculative execution here, where we're using the fact that this is delayed to test for these. Okay, everyone's still kind of with.
So is the goal just to binary search the target to figure out its value?
No, I can do one better than that.
Or is it to read the value from cache?
It is not to read the value from cache.
It's not cache coherence.
No, it is never the case that you can directly read this value. At no point can you ever directly read the hidden value. The CPU engineers have done a good job with security as a general rule. The only thing you can read is whether or not this shadow exists. So the thing on the board is still not Spectre, because Spectre is actually worse than this. But this is the main concept behind Spectre, which is why we're pausing here. Does everyone understand why I can use this to predict whether B is greater than or less than 3?
Why do we have to use 3 nested ifs for this?
Okay. This is easier to explain with the meltdown thing. Imagine this if is whether or not you have access to B. Imagine this was an access control search. This isn't quite accurate, but this is easier to understand, and it is somewhat in alignment with what's actually going on. Imagine this was an access control check. Now you're waiting for the access control check to come back, and then we do this execution, assuming the access control check will come back. Now, if you think about what I was teaching you about C and just how bad C is, C has this command called gets. Do not ever use this thing because it does not have a check on the array length. We talked a moment ago, though, about this is not what's executing on the processor, is it? This goes through a compile. So the compile will convert this into something that probably has an if checked in it, doesn't it? It has an if that says, am I past the end of my buffer? That may have been added by the compiler. That may have been added by the operating system that's making sure that you haven't progressed past the end. So if you think of this initial one here as whether or not this person has access, this isn't strictly required in Spectre, but it's much easier to understand. So now we're waiting, is the processor's waiting to see whether or not you're even allowed. Now, the processor doesn't do access control. So as a side effect, the processor does not see this as an access control statement. It sees this as simply a branch. It's from this thing's perspective, there is no distinction between an if involving an access control check and an if involving a number. Because the processor could not care less about security and it could not care less about access control. It just processes things. And it's something else's job to tell it what to process. So usually we have another unit sitting, okay, now we're getting below my level of knowledge on physical device. I don't know if it's a software or if it's a physical, but an MCU? Okay. It's been a while since I had to do the processor stuff. There's something else that is checking on accesses. It's checking on the access bits. The pages, as they're being loaded into disk, onto RAM, and etc. At those points, we're doing checks. And we're saying, okay, we've moved this on. Do you have access to this, yes or no? And that's being done a bit at the hardware level because we have access bits on everything. The access control is actually happening over here on those checks. But the processor will take the output of those searches. So if you try to access, if the processor says, oh, I would like access to this piece of memory, and it comes all the way back here it may say, well, no, this particular thing is not allowed access. It'll send an error back up to the processor. The processor processes that error. It will then do the same thing it does with branch prediction. It'll say, oh, you don't actually have access, roll everything back. Okay, we're still out here.
What if we remove line 1? Would it work better or worse?
Well, this possibly would not have passed earlier checks because you don't necessarily have access to it.
Ah,
B is somebody else's variable. It's the victim's variable.
understood. That makes sense.
It's not your variable.
That makes a lot more sense now. Good job.
Processors at any given moment may be processing more than one processes or threads worth of data. So it is possible it's interleaving processes from multiple different threads. And so it is normal for the processor to have a mix in cache between stuff you are allowed to access and you're not allowed to access. And this is one of the things that we're managing.
So basically the attacker, I mean, let's say there are two executions, parallel execution going on in CPU, right? And so the codes should be similar, right? Otherwise, the speculation how this is like a speculate. Let's say if the first code is running an if condition and then the registers have loaded something from cache, right? So that's sitting there now, and the next instruction would be from like someone else, and let's say the attacker's code, right? So now, if both the codes are not similar, then how would I know?
Codes are not similar. I'm trying to figure out what you mean by similar. Do you mean if they're not both using the variable B?
Exactly.
Okay, I'm saying B here for all of our sanity. It's actually a hardware address. And I can easily guess hardware addresses by simply adding a byte to them. So if I have access, we have not hit this point yet, but we're basically about to use a buffer overflow or buffer overread to guess somebody else's address. It's not hard to guess someone else's address. The cache is a physical thing. It goes from a certain value to a certain value, and that's it. All the randomization stuff we were doing elsewhere, that's all living in RAM and disk. It may just be living in disk even. When we hit the fast stuff on the cache and on the registers, we are now dealing with physical hardware addresses that are not randomized and are not virtualized. That means it is entirely possible to specify any component on cache and have it be loaded by the processor, which has ultimate control over everything. The only thing saving us from all of this is that when the request goes in, another unit is checking bits and is basically coming back to it saying, no, this wasn't allowed. And if it's not allowed, it rolls back because this is a solution to everything. If something goes wrong, it rolls back. It just rolls back. And there's a lot of the things processor engineers work on is how to make things just a little bit faster by either having a side cache, about guessing, figuring out how to do branch prediction with higher accuracy so that it can do this speculative stuff where it tries something, it doesn't know if it's going to work yet, but if it does work, we can go fast. And if we can get it to work more than half the time, or we can get it to work often enough, then we will succeed. Wow, it is 11:20. I have not actually hit Spectre.
27.
Huh?
27.
I'm sorry, I normally try not to hold you guys over. All right, we're going to talk about the actual last important step on Monday.
I'm trying to warn you. Sorry, I gotta take you back up.